going to go on and get started with today's lesson. So what we're starting today is Chapter 8. Chapter 8 is going to be over similarity. Now, everything that we're talking about with similarity is talking about things being similar from one to another. So when we talk about things being similar, it means they're going to be the same, but not exact. So, and we deal with this here because like a rectangle, we can draw a rectangle. Because we can say this here is a rectangle. Now this rectangle is similar to the board because they are both rectangles, but are they the exact same? Well, no, one is definitely bigger than the other. So when we talk about things being similar, they're not going to be the exact same size, but they're similar to each other, so other properties are going to be the same. Now our first section that we're talking about with similarities is corresponding parts of similar polygons. In this here, so we have this entire definition. ABC is similar to DEF. You can write ABC is similar to DEF as this here. Let's do an highlighter. Now this here does look very similar to our congruency statements when we said two figures were congruent, but the main difference is the sign in the middle. Because here we just have the one little squiggle line. This here is saying that they're similar. If we had equals, we're talking about congruency, them being the exact same. The sides, lengths, and the angles are all the same. Here, when we just have the one, we're saying that they're similar. They're not the exact same shape. They could have the same lengths, but we do know that the corresponding angles are going to be the same. The side lengths are proportional. That means one's going to be bigger than the other. So, the corresponding angles are congruent. For any figure that is similar, the corresponding angles have to be congruent. Because if we make something bigger or smaller, the overall angles don't change. So, well, because it is baseball season, if we think of a baseball diamond where home plate sits, the angle at home plate for a, what is it, I think the kids 8 and under, that angle that the home plate makes, is that the exact same as at the high school level? I mean the overall, where home plate sits. This angle here is going to be the same at 10 and under as it is for high school as it is for Major League, yes? Now, as y'all were saying, the overall field is bigger, yes? And the scale of it just changes. The overall angles at first, base, second, and third, how this figure is shaped, the angles at each one of those was staying the same. It's not automatically third base is a distance. The comparative distance between each of these bases is not miraculously between 10th grade or for 10 and under to Major League, like third base, its overall distance shot way out there into the outfield. No. The overall distance is all scaled up, yes? So the angles, all these angles here, from one to the other stay the same. And whenever we scale a figure, scale anything bigger or smaller, the angles value don't change. The lengths scale proportional, and we have a scale factor. Now the scale factor, if we're getting bigger, is going to be greater than 1. If we're getting smaller, it's going to be less than 1. And that's how we look at any of these here. So for any two figures that are similar, the angles are going to be congruent. We'll have congruent angles. They're going to be the exact same. But the side lengths are going to be proportional to each other. And we're going to have this scale factor K, what we're multiplying one side length to get to the other, or going back and forth. And that's really what we're going to start out looking at. Now, for this first example here, we're saying that these two figures are similar. We're saying that triangle RST is similar to triangle XYZ. RST and XYZ are similar. So the angles, as we just said, are going to be congruent. All the angles are going to be the same. Or the corresponding angles, sorry. The corresponding angles will be the same. So when we look at this here, RST is similar to XYZ. And they will match up that way. So R is going to match up to X. S is going to match up to Y. And T is going to match up to Z. Questions on this here? Pretty good. So that kind of answers part B, because we're saying that angle R, so we can write it down here, B, angle R is congruent to angle X. Angle S is congruent to angle Y, and angle T is congruent to angle Z, because these angles are going to match up this way. And we can really use those angles to also match up the sides. So here, the side length between R and T, 1 and 3, is going to match up to X and Z. These side lengths match up because they're going to be between the two sides, or two sets of congruent angles. Between 1 and 2, R and S is going to be the same as X and Y. And lastly, T and S matches up with our Z and Y. These are the sets of sides that match up, and their lengths, when we compare them, actually give us our scale factor, our corresponding set. And we can use these to write the ratios. Because if we want to write the ratio of sides, we're looking at RT and XZ. Yes. So we can say that we're comparing RT over our XZ. Is proportional to our RS over its corresponding or comparative side is XY is proportional to our last set of TS or ST and YZ. And we can say that these are equal. The side lengths aren't, but their proportion, their scale is still going to be the same. Scale from one to the other. Any questions on this so far? Now, the only thing we haven't found is the scale size. A, scale factor. Now, when we look at the scale factor, we're trying to see where are we going from and what are we going to. So we're going from RST to XYZ. RST to XYZ. Are the side lengths getting bigger or smaller? Smaller, because we're going from 25 to 15, or from 22 or 32. So our scale factor needs to be something less than 1. Because if it's greater than 1, it means it's getting bigger. If it's getting smaller, it needs to be less than 1. Now, the way that we can find the scale factor for any of these here is new over old. And this is the main way I remember it here. Because what is our new length over the old? Where are we going to? What did we come from? So looking at this here, well, we started at 25 and we went to, so the new, quote unquote, new length would be 15. Where did we come from? Because we're going from 25 to 15. Where we're going to, where we came from. And all we have to do is simplify this here. And we could type 15 over 25 into the calculator to see what that gives us. But they also, both 15 and 25 have a common factor of 5. If we reduce that, it would give us 3/5. And 3/5 would be the scale factor. And really what that's telling us is any of the lengths here for RST, if we multiplied them by 3/5, we would get the corresponding length of XYZ. Any questions on this here? And we can show you that here. So if we looked at it, say 20 times 3/5. If we multiply this out, it would be 20 times 3, which is 60. And then we would do 60 divided by 5, which would work out to be 12. 22, 12, which is what we wanted. And if we did the same thing with 30 and multiplied it by 3/5, well, 30 times 3 would be 90. And 90 divided by 5 is 18. It gives us the scale factor. Questions on this here? Okay, so we want to find the scale factor, we want to find all the pairs of congruent angles, and we want to write the ratio of the corresponding side lengths in a statement. Okay, now they told us ABC is similar to JKL. This is kind of nice because it goes on and pretty much gives us the angles. I don't know. Now, this statement here, ABC similar to JKL, gives us the angles that are going to match up. Now, angle A is going to be congruent to which angle? J. They're working somewhere. Now, B, guys, let's stay focused in here. Angle B is going to match up to which angle? K. And lastly, angle L, or angle C, is going to match up to angle L. So we can say for our congruent angles, well, angle A is congruent to angle J. Angle B is congruent to angle K. And angle C is congruent to angle L. And we really got that from our similarity statement. The similarity statement will really tell us what that is. Now, once we get our angles, it's kind of easy to match up the sides from there. Which sides are going to be corresponding? Well, if we look at AB, goes from the angle with 1 marker to the angle with 2, its matching side is JK, because it's the side with an angle with 1 marker to 2. It's the one that matches up. Then how about from B to C? Would be from K to L. And lastly, A to C would match up from J to L. And if we also look at the side lengths themselves, because if we look at ABC, 21 is the smallest, yes? Its matching side is JL. Well, 28 is actually the smallest length. They will keep to that pattern because the smallest side will match up with the smallest, the biggest with the biggest, and the middle with the middle. So if we want to write the corresponding ratios of sides, we could say that AB, and it matched up with what? Okay, J, because those are our matching sides. Because when we write this statement, our corresponding side lengths in a statement of proportionality, we're writing the sides that match up. So AB over JK. Since we start out with AB, we'll say BC, so, and AC as the sides on top. Once we pick side lengths of one triangle to be on top, we keep them on top for all three. Now, which side length matched up to BC? KL. And lastly, what side matched up to AC? And that would be our statement of proportionality dealing with the side lengths. So what's the only thing we're missing? The scale factor. The only thing we're missing is the scale factor from going from one to the other. And again, since they're similar, the scale factor for any of the sets of the sides will be the exact same. Because if we're scaling something, all the side lengths will be scaled in the same manner. Now we need to see where we're going. We're going from ABC to JKL. So we're going from 27 to, or 36 to 48, or 21 to 28. Now is it getting bigger or smaller? Bigger. So we expect whatever our scale factor, which they normally call K, to be greater than 1. So what's our new length, or one of the new lengths? 36. Which side did 36 come from, or compare to? EA, which is? So our scale factor for this here would be 36 over 27. Now we could plug this into the calculator to see if it reduces, and it does. And this here would reduce to 1.3 repeating, or as a fraction, 4 over 3. So our scale factor is 4/3. And that would be the answer. Now if we didn't pick 36 over 27, say I picked 48. Well, its corresponding side is? Well, 12 will go into both 48 and 36, yes? What times 12 is 48? What times 12 is 36? Isn't that the same scale factor we got with the other two? Okay. Well, that's the case. I'll just erase this here. Because the last one we had was 28 over 21, yes? Well, 7 will go into both of those, yes? How many times does 7 go into 28? 4. How many times does 7 go into 21? So we get the same scale factor. So no matter which sets of sides we pick, as long as we have the corresponding ones, we'll get the same scale factor. Any questions on this here? So again, we're doing the exact same thing with these here, and they tell us that JKL is similar to PQR. JKL, PQR. Well, that tells us that angle J and angle P are the same. Angle K and angle Q and R and L. They're going to match up like this here. So for our congruent angles, we can say what? Angle J is congruent to angle K is congruent to angle, and angle L is congruent to angle. So these would be our sets of congruent angles. We can go on and look at our proportional statement of sides for the side lengths. So what's one of our side lengths for our letters? KL. Can match up to QR, yes. Because we could use the angles to see how they match up, but also KL is the smallest side, and the smallest side in the other triangle is QR. Another set of sides. JL and PR. Or RP, PR, either one. And that leaves us with JK or JK, KJ or JK, and PQ or QP. Any questions on how we found the congruent angles or our proportionality statement? Now we just need to find our scale factor. And we're going from JKL to PQR. So we're going from here to here. So what side length, or what is one of the side lengths we can put in the numerator of our scale factor? 4. Not quite, because where are we going from to? We're going from JKL to PQR, so we would say 6. Because wherever we're going to should be the number on top, the side length on top. Where we're coming from should be the one on bottom. And its corresponding side would be 4. Because we would put the new side length on top, guys, and the old side length on bottom, and then we would reduce it. So this would reduce to 3 over 2. So our scale factor would be 3/2. We would have our congruent sets of sides and our corresponding sets of angles. Any questions on this here? All right. That actually brings us to the next part of this lesson here. If two polygons are similar, then the ratio of any two corresponding side lengths in the polygon is equal to the scale factor of the similar polygon. All the side lengths are going to have the same scale, as we already saw, yes? So, if we look at this here, DEF is similar to MNP. DEF, MNP. So we're saying that DE over MN is going to be similar to EF over NP, which is the same as DF over MP, because we can say that these side lengths are proportional, just like we did in the last one, yes? Could I also say that this is true? Because what's the difference between the one in green and the one in blue? I just flipped them all, yes? So did I really change the proportions in any of these? No. So no matter how we write either green or blue, it's still the same thing. We just need to make sure that the side lengths are all in the same spot. So the ones for DEF for the one in green are all in the numerators. For the one in blue, they're all in the denominator. We can't have them flipped. I can't have DE in the bottom of the first and then in the numerator of the second. We can't have that flip. As long as they're all either on the bottom or on the top, it is still the same proportion. And really, these here are just taking the place. DE is just taking the place of what? 15. DE is just saying that it's the length of 15 for this here, yes? DF is 20. EF is X. We want to find the value of X, yes? And we can use these proportionality statements to actually solve. And whenever we solve, really to make these easier on ourselves, we want to put what we're trying to solve for in the numerator. It's going to make it easier to work with. Okay? Now, what is the side length that corresponds with our length of X? It was our, what? 30. So 30 would go where? Under the x, because those side lengths correspond to each other. Well, now we need another set of side lengths that correspond to each other. Which one do we want to use? Gotta pick one. So we can pick 20, yes? Would 20 go on top or bottom? Top. Because x went on top, yes? We put x on top. 20, does it go with x or does it go with the other triangle? Is it with the triangle that has x or the triangle? It's the one with x, yes? Because x and 20 are on the same triangle. X is in the numerator, so 20 has to be in the numerator because they're with the same triangle. Now, we put 30 on bottom, yes? Its corresponding side is? Because we want the same proportion. X on top, so its corresponding, or the side that also is on the same triangle as x, which is our 20, would go on top. Any questions on how we set this up? Now, what we need to do next is solve for the value of x. Well, to get x by itself, we're going to multiply both sides by 30. Now, when we multiply both sides by 30, we multiply with the numerator. So here, we're going to do 30 times x, which will give us 30x over 30 is equal to, here we're going to do 30 times 20, which is 600. Now, I wrote this out for us to at least see the first time, because again, it's nice to see how this works. 30x divided by 30. 30 divided by 30 is 1. Anything divided by itself is 1. So these simplify to 1, leaving us with just. So the only thing we need to really find at this point is what is 60 divided by 24. That might have done 60 divided by 24. Would be my guess without looking at it. So our missing side length is 25. And that's it. Questions on this here? All right. Let's look at another one. In the diagram, GHM is similar to HKL. Find the value of x. So we know that these side lengths for these two triangles are proportional from one to the other. So if we're solving, it means we're going to have two fractions. And it's very helpful to have x in the numerator. And x is attached to this triangle here. What's another length on that triangle? 15. Because we need two lengths from the one triangle, and we need two lengths from the other. Now, what is the side length that corresponds to our side length of x? 12. What corresponds to our side length of 15? 10. GHM, GHM, HKL. So we match up and we match the side lengths. And when they give us these here, it's going to be good to figure out which ones match up, because just saying biggest to biggest, smallest to smallest doesn't always work, because, well, we don't really know how x lines up in this without the statement. Because it could be the biggest side, it could be the smallest, or it could be the one in the middle. We don't know what its length is. But here, based off this here, it's telling us that it matches up with our 12. It is going to be the middle side length. Now, what do we need to do next to solve? We need to multiply both sides by what? 12, because we're wanting to get the x by itself. We're wanting to get this variable by itself. And as we just saw with the previous one, when I multiply x over 12 by 12, the 12 over 12 will simplify to 1. Because when we multiply this here, 12 times x is 12x over 12 is equal to, here, we're going to multiply the 15 and 12 and get 180. Maybe that's what the calculator says. Well, anything divided by itself is 1. This will simplify to 1, leaving us with just x. Now on the other side, we have to do 180 divided by 10. I hope you can do that without a calculator. 18, because we drop a 0, because we just move the decimal place over 1. Because dividing by 10, we move it 1 to the right. If we're multiplying by, we move it 1 to the left. If we're multiplying by 10, we move it 1 to the right. If we're dividing by 10, we're just moving the decimal so that the number gets smaller. If we're multiplying by 10, we're moving it so it gets bigger. Yes? We like multiplying by 10s, which is the entire basis of the metric system. It's just multiplying or divided by 10. Any questions on this here? Okay. Let's look at this next one here. So we want to find the altitude. The altitude of a triangle is its height. So what it's actually asking for is this length here. Now again, we're talking about similar figures, and if we're solving, we're talking about two proportions, two fractions. And we know we want to find out what the length of x is, yes? What's a side length that's connected to our side length of x? Well, 20 would be where? Below x. So 20 and x would be connected, yes. So where would 8 be? Where we would set up 8? On bottom. Because 20 and 8 are together. X and what? X and 6. Now what do we do next? We need to multiply both sides by 20, because right now x is being divided by 20, because we have x over 20, x divided by 20. To undo division, we have to use multiplication. As we've seen on the last two, these two here will simplify to 1, which will tell us x is equal to 6 times 20 is 120 divided by 8. So our altitude PS is 15. So we can say that PS is 15. And we don't include the line segment above PS for this here because we're not talking about the segment itself. We're talking about its length. Questions on this here? Let's look at this next one. We have about 10 minutes left, yes? Yes. We're going to do two more. So we're going to do this one here. So we want to find the median ST. So they told us we want to find the length of ST. And again, they are similar. So we're going to have our two fractions. And we want x on top, yes? The side length that corresponds to x is what? 12. Because those are both the medians. Those are the two lengths that are similar to each other. Now, what length are we going to put on top of the other fraction? 36. And it's going to be over. Now what do we do? Multiply both sides by 12. Here the 12 and 12 will cancel out. They will simplify to, really they're simplifying to 1. Because 12 times 1/12 is 1. Now on the other side, we're doing 36 divided by 16 multiplied by 12, yes? So we could multiply 36 and 12 together. Which would give us 432. And divide that by 16 and get 27. Or, realistically, we could have just plugged that in, parentheses, 36 over 16, close parentheses, times 12. Hit enter and got our answer. And we get 27. Any questions on this here? And again, on the ACT or standardized tests like that, you want to just type it in like this here, because you're not losing points for not writing out every single step. And sometimes, especially if they give you the answers on the ACT, well, we know the scale should be the same, yes? Well, heck, we could have done 36 over 16, yes? And found out what that decimal is and wrote it down, and then just start dividing the answers by 12. Whichever one gives us the same decimal is the correct answer. Does that make sense? All right. So we're going to stop there. We'll finish these tomorrow. And yes, you got that one right. That one's actually, we can see it because we're trying to get to here, yes? We go from what, 6-2, 5-2, 8-2, so 4-2. Hey, sometimes we can see it.